Hello everyone, my name is Karel van Bockstal. What I'm going to talk about today is my work on inverse source problems for thermoelastic systems. I will start by explaining the results known for the heat equation. So during my presentation, omega will denote a bounded Lipschitz domain. This boundary is denoted by gamma. T is the final time. So we know about the forward problem that this is a well-posed one. If F belongs to this space and U0 is an element of H10, then we get the existence of a unique weak solution in the intersection of these two spaces. So in particular, we have that the solution U at the final time is well defined as an element of L2 omega. This is important for later. In inverse source problems, we usually assume that the source is separated in its variables. So f is supposed to be the product of a function g, which is depending on the space variable, and the function h, which is depending on the t variable, the time. So what we have here are two possibilities. The first one is inverse source problem 1, is that we suppose that h of t is given, that we would like to find g of x. In the second one, we suppose that g of x is given, and we would like to find the time-dependent part of the source. Let us first focus on the first inverse source problem. So the reconstruction of g of x. This can be done on the basis of the final time measurement of the temperature. This is denoted by psi of t. This inverse source problem can also be reformulated as an operator equation. A of g is equal to the measurement. And operator A is operator from L2 to L2, where we have that with g corresponds the solution of this problem at the final time t. So we know from the well-posedness result that this is an element of L2, so this operator is well defined. This is a classical example of an ill-posed problem, and the existence and uniqueness of a solution to this inverse problem is studied by many authors, and I will give now an overview of these results. So let us first consider the autonomous heat equation in this form. So the operator L here is a linear elliptic operator. A is a tensor. This is a coefficient C, and these are depending only on the space variable. We consider a homogeneous boundary condition, and in the right-hand side, we only see here the function g of x, so h is equal to 1. That for this problem, we can use a semigroup theory. We know that there is a closed formula for the solution, and using this formula, we can show that there is a unique solution to the inverse problem. This is done in the paper by Rundel. Let's now extend this result for a more general source where we have a product of H with G. We can show that there exists a unique solution if the operator L is self-adjoint one, and if we suppose that either H is strictly positive or strictly negative. In that case, we have the uniqueness of a solution. When H changes its sign, then it's possible to construct a counterexample that violates the uniqueness of a solution. Next, I will show you another approach for showing the uniqueness of the solution. It's a variational approach. And the main idea is that you multiply the PDE with this fraction, so the time derivative of u divided by the time-dependent part of the source. And then we see easily that the right-hand side term cancels out because the final in time measurement is equal to 0 and the initial temperature is equal to 0 when we consider uniqueness for this problem. So then we need to keep the two terms in the left-hand side positive, and this is the case if the derivative of h is positive. So we assumed here that h is strictly positive to be able to divide by h, and together with this condition we have also, when we follow the variational approach, the uniqueness of the solutions. So, but in comparison with the semigroup theory, we get an additional condition on the derivative. But I will explain immediately that this approach can be useful because when the coefficients in the operator L defined on both the space and the time variable, so we have an operator L of t here, then there is no representation formula for the solution available. And we need to use an alternative approach in the semigroup theory. And so then, for instance, it's a possibility is to use a variational approach. This is done in this article of Dyer for the case that h is equal to 1. And under these conditions on the tensor A and on the coefficient C, the author showed the uniqueness of a solution. Previously, Isakov showed already under these conditions the uniqueness of a solution when there is a more general source h. So we have that h is strictly positive and monotone increasing, or that h is negative and monotone, strictly negative and monotone decreasing. So when one of these two conditions holds, then the solution is unique. And this is the same condition as we saw before when using the variational approach. And this approach is later used to extend the class of solutions to functions being monotone in time. The idea here was to rewrite the PDE into a new unknown v, which is u divided by h. So we suppose that h is nowhere 0 in the given time frame. And then the time derivative of u divided by h can be written in this form. And you can easily see when following variational approach that this coefficient alpha here, which is the derivative of h divided by h itself, the derivative of it should be negative. So this in this article, the class of admissible function is extended to also, for instance, concave functions. So, but to make clear, there are functions satisfying the conditions of the theorem of Isakov and not satisfying this condition here and the other way around. So let's explain now the differences when considering the wave equation. So we have here a second order time derivative of u. Then Isakov showed that h should be positive, but also its derivative should be strictly positive. So if in the case h equal to 1, there is no uniqueness of a solution. There's a counterexample constructed by Isakov, and there is uniqueness in the case that there is an additional damping term into the equation. So if we look at a more general wave equation with coefficients rho and mu here in front of the time derivatives, then we have uniqueness under these two classical conditions. So also constant h is included when there is when the coefficient mu is non-zero. And alternatively, you can also use for the wave equation the variational approach. So this is again alpha. And under these conditions on alpha and the coefficients, you have also the uniqueness of a solution to the inverse source problem. So this was about the theoretical results. This is here one slide about the numerical reconstruction of the heat source. In our article of Hazanov and Johansson and Lesnick, where they try to recover the source by minimizing this functional. And also Johansson and Lesnick proposed an iterative procedure, which is of Landweber-Friedman type and consists out of a sequence of well-posed direct problems for reconstructing the non-source. Okay, let us now focus on the second inverse source problem, the reconstruction of the time-dependent part of the source. This can, for instance, be done on the basis of this energy measurement. This omega function is called a weight function. And the basic idea here is that we multiply the PD with this function and then integrate the equation over the space domain. So we will have to assume here that this integral is not equal to 0. And depending on the boundary condition, there are it's a different situation. Cannon and Lin consider the homogeneous Neumann boundary condition and obtain this expression for the source H in terms of the measurement and the function u. So when you apply Green's theorem here with homogeneous norm and boundary condition, the boundary term cancels out, and we need that this weight function omega belongs to H1. Prilepko considers the case that U is 0 on the boundary, then you get this expression for H of t, but you need to assume to get rid of the boundary term that W belongs to the space A, sublet space H1 0. You can also apply one time more Green's formula, but then you need to assume that omega also belongs to H2. You can show the uniqueness by using energy estimate approach. So what you can do is take the absolute value of H of t, and depending on the situation, this will be estimated by the L2 norm of U or the L2 norm of the gradient of U. So A is the measurement is 0 in the proof of uniqueness. And then you use the solution as a test function, and you can apply epsilon Young's inequality to put a small weight on the source, and then you use this estimate together with the Cromwell lemma to obtain that U is equal to 0, and then also, of course, from the expression of H, you can get that H is equal to 0, and you get a uniqueness of a solution. In the case of a self-adjoint operator L and homogeneous Dirichlet boundary condition, you can also, so imported here, L is only is the elliptic operator only depending, or the coefficients only depend on the space variable. You can also obtain via semigroup theory and a Volterra equation of the second kind, and so also get a unique solution to the problem. So the aim was to extend these results to a coupled system of hyperbolic parabolic equations. So this is a classical thermoelastic system for isotropic material. So all coefficients are positive constants. P is a load vector, H is a heat source, U is denotes the displacement, and theta is the change in the temperature from a reference value T0. So this symbol here denotes the convolution product in time. So usually this convolution is exponential function of this form. There are three types of thermoelasticity, and the distinction is made on the basis of the heat equation. So if we only have the term with the Laplacian, then we have type 1 thermoelasticity. When we have the convolution term here, but the thermal conductivity is equal to 0, then we speak about type 2 thermoelasticity, and when both terms are incorporated into the equation, then we speak about type 3 thermoelasticity. So these were the results available in the literature before I started my work. Belasuth and Yamamoto studied the inverse problem of determining space-dependent heat source on the basis of the measurement of the displacement on the surrounding on the subdomain containing the boundary of omega, and also they measured also the temperature at a fixed time point into the complete domain. Wu and Liu studied the determination of the space-dependent load source for type 2 thermoelasticity from a displacement measurement on this same subdomain, as in the paper of Belasuth and Yamamoto. In both papers, the Kalman estimate is used, which gives some Hölder stability for the inverse source problem and also the uniqueness of a solution, but there are no numerical schemes to reconstruct the unknown source. What's important, of course, is that the forward problem is well posed. Under these conditions on the sources and the initial data, we have that the solution U and theta belongs to the intersection of these spaces. So we see here also that U at final time is well defined, and also theta at the final time is well defined as an element of L2. But when using the variational approach, we need that the function, the time derivative of the solution, for instance, for the displacement, and also some problems for the temperature belongs to to this space. So the space L2 in time, H1 0 in space. So here we have only the L2 regularity in space for the time derivative of u under this initial condition. So what we exactly need here is that the PDEs are fulfilled at the initial time. So in that case, we have that the time derivative of u belongs to this space. Okay, the first inverse problem is the identification of space-dependent sources. So the problem we considered is, can we uniquely determine space-dependent load source of heat source from the final in time measurements of the displacement or the temperature, or from the time average measurement of the displacement and temperature. And we would like also to obtain numerical schemes for computation. So these are examples of ill-posed problems, because small errors present in the measurement can give rise to large errors into the solution. So the first solution we obtained was the reconstruction of a space-dependent load source under the presence of an additional damping term in the equation. So from the final in time measurement of the displacement. So, but we needed an additional damping term as considered also before for the wave equation. And this damping term is also considered by other authors. The results of this article are published in Inverse Problems in Science and Engineering, and are later extended to an isotropic thermoelastic system in cooperation with Professor Marren in computer methods and applied mechanics and engineering. So what we need here is that function g is strictly monotone increasing, and in the case that g is linear, we extended the iterative procedure by Johansson and Lisnik for the heat equation to this thermoelastic system. So in that case, we could develop a stable iterative algorithm for the reconstruction of the load source P of x. Then now we are studying more general sources, so that we have also the product of the function g with the given time-dependent function h, also for the temperature source. And the first problem we could solve is this one. So we want to find space-dependent load source on basis of the final time measurement, and this is possible if g is strictly positive, but also its derivative is strictly positive. We use the variational approach, so here it's needed that the time derivative of u belongs to this space, and we see that we get the same monotonicity conditions on h as obtained for Isakov for the wave equation. We tried also to use the variational approach used by Slodicka and Johansson in their paper, but then when you make the substitution to the new variable, these coupling terms make problems, and it doesn't seem possible to obtain the uniqueness of the solution. So definitely this is an interesting direction for future research. Secondly, we have showed also that g of x can be reconstructed in a unique way from the time average measurement of the displacement if h is strictly positive or h is strictly positive. And here we need no additional assumptions on the solution. For the temperature source, we can reconstruct g of x only from the average measurement of the temperature. So it's still an open problem to reconstruct g of x from the measurement of the temperature at the final time t. Again, the coupling term is, so the terms containing the coefficients gamma are causing problems. This result is valid when h is strictly positive and its derivative is positive, or also when this condition is satisfied. So also here, it's necessary that you have this regularity on the solution. The results of this research are recently submitted together with a PhD student of me, Frederik Maas. So now about the identification of time-dependent sources. So the problem we considered is to reconstruct the time-dependent heat source on the basis of this additional integral measurement. So again, we consider a weight function, and this is a thermoelectric system as before, and we will specify immediately the boundary conditions. So the first result we obtained was in one dimension. When the weight function was equal to 1, then we get this expression for the temperature source, and to taking advantage of the one-dimensional setting and also on the boundary conditions, we considered that theta is 0 on the boundary and the derivative of u is 0 on the boundary. Then we could show the existence and uniqueness of an exact solution to the problem. So in the case of exact theta, this is published also in inverse problems in science and engineering. But this approach seems not possible to be extended to general dimension, because then you need to keep the integral over the domain of the Laplace operator of theta under control. This is difficult. So, but an alternative approach here is to follow the ideas from Cannon and Prilevko before, is that we transfer derivatives to the weight function. So in the case of a normal boundary condition, you can get this expression for h of t. So a weight function belongs to h1. So this integral should be non-zero. And the Dirichlet boundary condition, in the case of theta is equal to 0, we get this expression for h of t. And then you need to assume that the weight function is 0 on the boundary, so you assume that it belongs to this space. So again, we can show existence and uniqueness of a weak solution for exact theta. And this includes a numerical algorithm for computations. The analysis is quite complex due to the coupling of the equations, and is together with Professor Marin of the University of Bucharest, and is also recently submitted. So for future research, we would like to relax assumptions on the heat source when looking for a space-dependent on the time-dependent part of the source when looking for a space-dependent source. And also interesting is the determination of a space-dependent heat source when considering the finite and time measurement. So this is still an unanswered problem at the moment. And of course, also the focus will lie on the further development of numerical methods for the reconstruction of the unknown sources. I thank you for your attention.